Hey guys, welcome to my third physics lab report. Today, we will be discussing Newton's second law in regards to circular motion. As we discussed in previous labs, Newton's second law explains that the force applied to an object is equal to that object's mass times the object's acceleration. This concept becomes a little more complicated when applied in a circle. In this instance, the force applied to an object is broken up into two components, which each contribute to the direction and the speed of the object. As the force moves in a circle, the perpendicular net force points towards the center of the circle and determines the direction of the moving object. The parallel net force points either parallel or anti-parallel to the direction of the momentum and determines whether an object is speeding up, slowing down, or maintaining the same speed. Together, the parallel and perpendicular components of the net force add together to create the total net force. This concept is a lot easier to visualize when looking from a geometric perspective. If an object is traveling in a circle like this, the perpendicular force will point towards the center of the circle, the parallel component will point in this direction, and the net force will split the difference between the two. This brings us to the goal of our experiment. In this week's lab, we were tasked with finding the mass of a black hole given the orbital motion of a star around that black hole. I want to take a moment to discuss some of the code I made to represent this. The first thing I did was adjust the seed by inputting my email address to get my set of data for the orbit of the star. Next, after skipping a boatload of code that did some stuff, I set the mass of the star to match the mass given in the experiment instructions and adjusted the change in time to be the length of a day in seconds. Next, I inserted the equations for initial and final momentum, the change in velocity, and the change in momentum. Next, I calculated dp dt, which I then applied to the net force, since those values are equivalent. Using the initial momentum, I was able to calculate the unit vector of momentum, p hat, that I would need to use later. After that, I calculated the magnitude of the net force and then multiplied it by p hat to get the value of parallel dp dt. I applied that value to its equivalent, the parallel net force. Since the total net force is the sum of the parallel and perpendicular net forces, I was able to simply subtract the parallel net force from the total net force to get the value of the perpendicular net force. Similarly to before, I applied the value of dp dt perpendicular to the perpendicular net force. Finally, I was able to use all the calculations I had made and find the mass of the black hole using the gravitational force equation. The last thing I did was create arrows to represent the parallel, perpendicular, and total net forces acting on the star. After I finished up all the coding, I ran my model to get my data for the calculations I had done earlier. You can see the model star traveling on an elliptical path around the black hole and the arrows corresponding to the net force and its components. Notice that the arrows vary in size and direction as the star travels further along its path. The changes in size result from the black hole not being located in the center of the path and the path itself not being circular. As the star gets closer to the black hole, the gravitational force from the black hole pulls stronger. The direction of the force arrows also originate from the black hole. Since the black hole is exerting a force on the star, the gravitational force will always be pointing towards the star, thus causing the force to reorient itself at each time step to remain towards the black hole. Looking at the data, the first data to appear was a stream of values estimating the mass of the black hole at each time step. I averaged the values together to create a rough estimate of the mass, which was 1.21 times 10 to the 34th. After all these lines and lines of mass estimations, the magnitude of the forces appear. You can see the total net force, the parallel net force, and the perpendicular net force. As I explained while looking through my code, the total net force and its components is equal to dp dt, which is the rate of change of momentum of the object. This means that the rate of change of momentum will have the same magnitude and direction as the total net force and its components. This process would apply for any object that exerts a force on our star. Even if the black hole was replaced with a different black hole, we'd still be able to calculate that black hole's mass, even if the trajectories were exactly the same. As for telling the difference between these two identical trajectories, if the mass of the black hole was changed, then the mass of the star would have to change as well to maintain that same trajectory. Because of the gravitational force equation, if you were to double the mass of the black hole, then you would half the mass of the star to maintain the same trajectory. So that about wraps it up for today. Tune in next time for more science experiments.